Welcome to Chapter 5 on aromatic compounds. In this section, we'll explore one of chemistry's most fascinating molecules, benzene. We'll examine its unique structure, understand why it's so stable, and discover how chemists create it in the laboratory. By the end, you'll see why benzene is far more special than its simple formula, C6H6, might suggest. Benzene's structure is the key to understanding its behavior. According to Kekulé's model, benzene has 6 carbons arranged in a ring, each bonded to a hydrogen atom. The carbons alternate between double and single bonds. However, X-ray crystallography reveals something remarkable. All carbon-carbon bonds in benzene are identical at 0.139 nanometers, intermediate between a single bond and a double bond. This is explained by resonance. Benzene doesn't flip between two structures. Instead, it exists as a hybrid where 6 electrons are delocalized around the entire ring. These delocalized electrons are not locked to any specific pair of carbons, giving benzene extraordinary stability. Thermochemistry provides compelling proof of benzene's exceptional stability. When chemists measure the heat released when benzene is hydrogenated, adding 3 hydrogen molecules to convert it to cyclohexane, they get negative 208 kilojoules per mole. If benzene were truly 3 separate double bonds like cyclohexatriene, the calculation would predict negative 360 kilojoules. The difference of 152 kilojoules represents resonance energy, the extra stabilization from electron delocalization. This enormous energy difference explains why benzene doesn't behave like a typical alkene. It's not just more stable, it's fundamentally different in how its electrons are organized. The delocalized pi electrons make benzene chemically inert in ways that surprise many students. Because those electrons are shared equally around the ring, benzene resists addition reactions, the typical behavior of alkenes. Instead, benzene undergoes substitution reactions, where a hydrogen is replaced rather than the ring being opened. This preference for substitution over addition is a hallmark of aromatic compounds. The delocalization protects the ring from attack. Only under extreme conditions, like intense ultraviolet light or with special catalysts, can benzene be forced into addition reactions. This chemical reluctance is a direct consequence of that 152 kilojoules of resonance energy holding the ring together. Now we're looking at electrophilic aromatic substitution, a fundamental mechanism in benzene chemistry. When an electrophile, like an acylium ion or nitronium ion, approaches the benzene ring, it attacks the pi electron cloud. The ring's electrons are drawn toward the electrophile, creating a positively charged intermediate, where the positive charge can be distributed across 3 different carbon atoms through resonance. Finally, a hydrogen atom is lost, restoring aromaticity and forming the substituted benzene product. This mechanism is central to understanding how benzene derivatives form. Benzene can be formed through several important synthetic routes. One method involves heating benzene with zinc oxide as a solid reactant. Another uses zinc metal directly. A third relies on thermal decomposition. Beyond these, benzene is also prepared through decarboxylation of benzoic acid, removing the carboxyl group, or by reduction of phenol. Additionally, catalytic reduction using various hydrogels or charged species like nitronium ions can generate benzene. Each method exploits different chemical properties and reaction conditions, making them useful in different synthetic contexts depending on starting materials and desired conditions. Now we're moving into the detailed mechanism of electrophilic aromatic substitution. This is a 2-stage process. First, the electrophile, the electron-loving species, must be generated or activated. Then it attacks the pi electrons of the benzene ring, creating a carbocation intermediate. Finally, the system restores aromaticity by losing a proton. The key insight here is that the aromatic ring acts as a nucleophile, attacking the electrophile. This is fundamentally different from aliphatic chemistry because the benzene ring's stability depends on maintaining that 6-pi electron system. The electrophile doesn't just appear on its own, it must be generated. In nitration, sulfuric acid protonates nitric acid to form the nitronium ion, NO2+, which is an extremely powerful electrophile. In halogenation, a Lewis acid like ferrite bromide polarizes the BRB bond, creating a partial positive charge on bromine. These Lewis acids are crucial because they activate the reagent, making it electrophilic enough to attack the relatively stable benzene ring. Without them, the reaction either doesn't happen or proceeds extremely slowly. The carbocation intermediate is the critical point. When the electrophile attacks, one carbon of the benzene ring becomes sp2 hybridized and positively charged. Now here's the crucial part. This positive charge doesn't stay localized on one atom. It's distributed across 3 different resonance structures delocalized around the ring. This resonance stabilization is what makes the reaction work. Without it, the intermediate would be far too unstable. Finally, a base removes a proton from that same carbon, restoring the aromatic pi system and completing the substitution. Aromatic halogenation is the process of adding halogen atoms, chlorine, bromine, fluorine, or iodine, to benzene rings. Unlike alkyl groups, halogens are electron withdrawing, meaning they pull electron density away from the aromatic ring. This makes the ring less reactive overall, so halogenation is a deactivating reaction. However, halogens are ortho-para-directors, meaning they guide the next incoming electrophile toward the ortho and para positions relative to the halogen already on the ring. The reaction requires a Lewis acid catalyst like aluminum chloride or ferric bromide to activate the halogen. The mechanism begins when the halogen molecule, say Cl2, reacts with the Lewis acid catalyst AlCl3 to form a highly polarized Cl+ electrophile. The benzene ring's pi electrons then attack this electrophile, forming a carbocation intermediate called an uranium ion. This intermediate is stabilized by resonance, with the positive charge distributed across 3 positions on the ring. Finally, a hydrogen is removed from the carbon that attacked the electrophile, restoring the aromatic ring and releasing HCl as a byproduct. This 3-step process is typical for all electrophilic aromatic substitutions. The reason halogens direct ortho and para is rooted in resonance stabilization of the intermediate carbocation. When the electrophile attacks at the ortho or para position, one of the 3 resonance structures places the positive charge directly on the carbon that bears the halogen. Even though halogens are electron withdrawing overall, their lone pairs can donate electron density to stabilize this positive charge through resonance. This stabilization makes the ortho and para intermediates more stable than the meta-intermediate, where the positive charge never sits adjacent to the halogen. Because the ortho and para intermediates are lower in energy, they form faster, making ortho and para the major products. Even though halogens direct ortho and para, they are deactivating groups. This means halogenated benzenes react much more slowly in electrophilic aromatic substitution than benzene itself. The reason is that halogens are highly electronegative and withdraw electron density from the ring through inductive effects. This reduces the electron density available for the pi system to attack an incoming electrophile. So while the ortho and para positions are still preferred, the overall reactivity is suppressed. This is why multiple halogenations require forcing conditions, high temperatures, excess catalyst, or extended reaction times. It's important to distinguish between directing effects, which tell you where substitution occurs, and activating or deactivating effects, which tell you how fast the reaction goes. When a benzene ring has multiple substituents, their directing effects can either reinforce or compete with each other. The hierarchy of directing effects is activating groups override deactivating groups. So if you have a methyl group, which is activating and ortho-para directing, and a nitro group, which is deactivating and meta-directing, the methyl group wins. The incoming electrophile will be directed ortho and para to the methyl group, not meta to the nitro group. When both groups have the same directing preference, like 2 meta-directors, they reinforce each other and make the preferred position even more obvious. And when both are ortho-para directors, the more strongly activating one dominates. These rules help predict where substitution occurs in complex molecules. The reactivity of different halogens in aromatic halogenation follows a clear trend. Fluorine is by far the most reactive, followed by chlorine, then bromine, and finally iodine. Fluorine's extreme reactivity comes from its small size and high electronegativity, which makes the FF bond weak and the F+ electrophile very reactive. Chlorine is the workhorse of aromatic halogenation in the lab. It's reactive enough to work well, but not so reactive that it's dangerous or hard to control. Bromine is less reactive and often requires heating or more catalyst, but this can actually be an advantage when you want selectivity. Iodine is so unreactive that it's rarely used for direct halogenation. This reactivity order is important when predicting which halogen will react first in a mixture or when choosing conditions for a specific halogenation. Let's work through some concrete examples to see how these directing effects play out. In the first example, we have a benzene ring with both a methyl group and a nitro group. The methyl group is activating and ortho-para-directing, while the nitro group is deactivating and meta-directing. Since activating groups override deactivating groups, the methyl group wins, and the incoming electrophile is directed ortho and para to the methyl group. In the second example, we have a carboxylic acid and a sulfonic acid group, both meta-directors. They reinforce each other, so the incoming electrophile is directed to position 3, which is meta to both groups. In the third example, we have a methyl group and a chlorine atom, both ortho-para-directors. The methyl group is more activating, so it dominates, and substitution occurs ortho to the methyl group. These examples show how to apply the directing effect rules systematically to predict products. Halogenation and nitration are both electrophilic aromatic substitution reactions, but they differ in important ways. In halogenation, the electrophile is a halogen cation like Cl+ or Br+, activated by a Lewis acid catalyst. In nitration, the electrophile is the nitronium ion, NO2+, generated from nitric acid and sulfuric acid. Both reactions are deactivating. They make the ring less reactive to further substitution. But here's the key difference. Halogens are ortho-para-directors because their lone pairs can stabilize the intermediate carbocation through resonance, even though they withdraw electrons overall. Nitro groups are meta-directors because they have no lone pairs to offer stabilization, so the meta-intermediate is actually the most stable. Understanding this distinction is crucial for predicting products in polysubstituted aromatic compounds. Aromatic halogenation is a fundamental reaction in organic chemistry that combines electrophilic aromatic substitution with the unique properties of halogen substituents. Remember that halogens are electron withdrawing, which makes them deactivating groups. They slow down the reaction. But they're also ortho-para-directors because their lone pairs can stabilize the intermediate carbocation through resonance. When you're predicting products in polysubstituted benzenes, always apply the hierarchy. Activating groups beat deactivating groups, and ortho-para-directors beat meta-directors. Finally, keep in mind that directing effects and activating-deactivating effects are two separate concepts. A group can be a strong ortho-para-director but still deactivate the ring. Understanding these principles will help you predict products accurately and understand the mechanistic reasoning behind them.